Welcome to a new lesson of heat transfer. Today we start talking about thermal radiation. Thermal radiation is defined as a transfer of thermal energy via electromagnetic waves. So this mechanism of heat transfer is completely different from conduction and convection because it can happen in a vacuum, while conduction and convection require a medium. James Maxwell in 1864 first established the theory of these electromagnetic waves. So let's see a few properties of these waves. They travel at the speed of light. So in a vacuum, the speed of light is usually indicated by c, and that's 3 times 10 to the 8 meter per second. Electromagnetic waves are characterized by frequency and a wavelength, and the wavelength can be computed as the ratio between the speed of light and the frequency. The typical wavelength of electromagnetic waves that transfer thermal energy is about 1 micron, that's 10 to the minus 6 meters. But electromagnetic waves can have all sorts of wavelengths. So wavelengths can vary continuously, so they belong what's called electromagnetic spectrum. So waves with different wavelengths have the same physics, but they have different origins and different uses. So let's see some examples. For example, electromagnetic waves, they have a wavelength of about 10 to the 7 or 10 to the 8 microns. These are radio or TV waves. Instead, electromagnetic waves with a wavelength that belongs in this range, so 10 to the 3 or 10 to the 4th microns, these are microwaves. And that's the range that it's interest for us. So that's the range of wavelength of waves that transfer thermal radiation. That's for wavelengths between 10 to the minus 1 and 10 to the second power microns, whereas X-rays have a wavelength between 10 to the minus 5 and 10 to the minus 2 microns. So as I said, thermal radiation is transported by electromagnetic waves with wavelengths in this range. And heat is continuously emitted by radiation by any surface. So any surface with a temperature that's larger than 0 Kelvin emits thermal radiation through the vibration of the particles. So we can say that all objects transfer thermal radiation. In the portion of the electromagnetic spectrum that transfer thermal radiation, we can define this wavelength in 3 different groups, 3 different groups that are classified as infrared, visible, which is light, and part of the ultraviolet range. And within the visible part of the spectrum, that's for wavelengths 0.4 to 0.76 microns, we can further subdivide this range in different colors. And the sun is considered, of course, the primary source of thermal radiation, and the electromagnetic waves emitted by the sun are in this range, so 0.3 to 3 microns. About half of the electromagnetic spectrum emitted by the sun is light, and the rest is shared between infrared part of the spectrum and ultraviolet. In general, thermal radiation is a volumetric phenomenon, means that any object emits a thermal radiation from any point, so even in the interior, but in our lessons, we can approximate a thermal radiation to be a surface phenomenon. So we're just interested in the radiation that's emitted from a surface. And usually we consider the surface to be uniform, with uniform properties. So radiation is emitted at any point in the same way, and it's very flat. So of course, to determine the thermal radiation, we need to know the temperature of the surface. A central concept in the study of radiation is the black body radiation. As we said before, all the objects, all the bodies emit radiation, but the crucial question is, what's the maximum thermal energy emitted at a given temperature? So that's what's called the black body radiation, indicated by EB, and the units is watts divided by meter squared, and that's sigma times T to the 4th power, where sigma is Stefan Boltzmann constant, and T is the temperature of the surface. So note the 4th power. So what are the properties of a black body? Black body can be defined as a perfect emitter and a perfect absorber. So the maximum radiation emitted, it's exactly the radiation emitted by a black body. And a black body is also a perfect absorber. This means that it absorbs all the thermal energy that arrives through radiation from the environment. Black body is also diffuse. This means that radiation is emitted in all directions in the same way. And the formula here, EB equals sigma T to the 4th power, is the power per unit area emitted by the black body and includes all the wavelengths in the spectrum. So since all the wavelengths are included in the formula, a natural question to ask is, how is the energy distributed across all the wavelengths? The answer to this fundamental question was answered by Max Planck, Nobel Prize laureate in physics, and he was able to arrive this formula in 1901, and that's what's called now the Plancks Law. So it has this formula. We don't have to remember this by heart. And C1 and C2 here are two constants. We can see the EB lambda, which is the spectral body emissive power, depends on the wavelength now and also on the temperature. And you see here lambda and the temperature appearing in the formula. What we can do, we can sketch this function here as a function of lambda. So we can represent Planck's law graphically. So we note first of all here that EB lambda and lambda here, the two scales are in the log scale, and the typical graph has this form. We can see that the distribution is continuous function of lambda. If the temperature is increased, then the emissive power is increased. Another property of this distribution is that if the temperature of the surface is increased, then the best lambda, which is the lambda at which there is maximal power emitted, decreases. And the sun is right here. So the temperature is about 5800 Kelvin and is also in the visible range. So we can say, of course, then the sun gives us light, so the ability to see, but also, of course, it gives us energy through radiation. And you've noted here this dotted line that connects all the points of the maximum points. So all these points here are the maximum, for each temperature, the maximum emitted power, and also define the optimal wavelength. And the dotted line mathematically can be expressed through the Wien's displacement law. that was actually found before the Planck's law, that was found Wines in 1894, and says that the product between the optimal wavelength and the temperature of the surface is equal to a constant, this constant. So if we know the temperature of the surface, then we also know the optimal wavelength. So the wavelength at which the maximum thermal energy is emitted by radiation, by a black body. So once we know the spectral distribution of black body radiation, then we can recover back the power, the total power emitted by a black body per unit area. So all we have to do, we have to take the EB lambda. So we saw the Planck's law as a function of lambda in T, and then put it here inside this integral. And then we integrate from 0 to infinity because we want to integrate the spectrum across all the wavelengths. And we obtain the EB, the power, black body power. So a very interesting exercise mathematically is to substitute the formula for Planck's law in the integral and try to do this integral. I can just give you a hint, and it involves a series expression if you want to solve it. Now finally, if you're instead interested in only the portion of the electromagnetic spectrum, we want to compute also only a partial emitted power. So for example, in the range between 0 and a certain wavelength lambda, all we have to do, so let's indicate this by lambda bar, all we have to do is to integrate EB lambda across the wavelength, but just from 0 to lambda bar. So this concludes our first lesson on thermal radiation, and I'll see you in the next class. Thank you very much.